All right, so the Leonard-Jones potential energy graph. First of all, what sort of potential energy are we talking about? What types of interacting objects are we discussing here? We're usually talking about, potential energy requires some sort of interaction. Yeah, typically two atoms or two molecules, two small particles. So we've got, let's say, a particle and another particle. And we're talking about the interaction between them. And we're specifically assuming neutrally charged particles. If they were both positive or both negative, or one positive and one negative, if they've got this difference in charge, then the electric forces are going to be the most important forces in between them. So the graph would look very different. But we're assuming here that they are neutrally charged. Each one has equal numbers of protons and electrons. They are still going to be exerting forces on each other if they're close enough to really interact. For instance, if the molecules are way too close, what would you expect to happen? What would these molecules do if they're really close to each other?
They'd repel.
Yeah, if they're really close, they're going to repel. And the reason for that is ultimately the electrical forces anyway. Even though they're neutrally charged, if you look at where the charges are, you've got positive charge in the nucleus in the middle and negative charge around the exterior. If they get too close, the electron shells starting to overlap is really what's going to be driving this repulsive force. So if they're too close, they repel. Which means the force counts as positive, a positive force causing them to increase the distance. So we say force is positive, greater than 0. But if they get further apart, atoms don't just keep repelling each other forever. If they did, matter wouldn't stick together. And in everyday experience, matter, at least solids and liquids, do tend to clump together. We get clusters of particles. So if they get far enough apart, the electric repulsive forces gets weaker and weaker, but we get another force causing them to cling together. So molecules that are reasonably close, not too close, do attract each other. So if they're not so close, we get an attractive force, which we're going to treat as a negative force. Negative in the sense that an attractive force is trying to pull them back together, trying to decrease the distance. And the R here on this graph really does just represent the distance between particles, generally measured from center to center. So that's what R signifies here. R is the distance from center to center, the radial distance from one center out to the other center. So if R is too small, we get a repulsive positive force. If R is bigger than that, significantly bigger than that, we get an attractive negative force. Also, what would you expect about the forces if they're very far apart? If atoms are extremely far apart, what would you expect to be true about the forces between them? Yeah, it goes to 0. You get almost no interaction at all. And physically, or mathematically anyway, they're always interacting at least a little bit. No matter how far apart the atoms are, there is some force. But that force gets weaker and weaker the further apart the molecules get. And that's generally true for any long distance force. Any force that can act at a distance is going to get weaker and weaker the further apart the objects get. Whether it's gravity, electrical force, magnetic force, these forces, they all get weaker as the objects get further apart. But that means there's going to be some equilibrium distance, some distance where they're not too close to repel, but they're also not far enough apart to attract. There's some distance, some sweet spot on the R values where that's exactly equilibrium. The attractive and repulsive forces balance out. And we typically call that R naught. So there's some distance R naught. That's the equilibrium distance where the forces balance out. At that location, the force is 0. And what does force tell you about the potential energy graph? What's that relationship between force and the potential energy graph? Force equals what? Yeah, it's the magnitude of the slope. And we can also even specify a direction there. Force is the negative, the opposite of the slope. Force is the opposite of the slope of the potential energy graph, that is the derivative. So if we have a location where the force is 0, that means the potential energy graph has to have slope 0. In other words, it has to reach a maximum or a minimum. So at this location, at this R value, the graph has to be flat. So the graph has to be flat here. In other words, it has to reach a max or a min. If R is small, if the particles are too close, they repel. The force is positive, trying to repel them, which means the slope would have to be, slope is going to have to be negative. So in this region, if they're too close, we get a negative slope because we have a positive force. And if they're further out, if the particles are not so close, we get an attractive force, that is a negative force, which means a positive slope. So we should expect the graph to look something like negative slope, then flat, then positive slope, which suggests that at R naught, we've got a minimum. It's getting a decrease in potential energy, then levels off, then an increase in potential energy. And furthermore, since the force gets weaker and weaker as they get further and further out, we should expect this positive slope to flatten out. We're going to get less and less and less steep. On the other hand, if we try to push the particles closer and closer together, can you push two atoms so close that they actually overlap and become the same location? No, that's impossible. The closer you push them, the more pushback you get. The repulsive force just gets stronger and stronger without limit, which means as you get closer and closer, R shrinking, this force, the potential energy graph has to just get steeper and steeper. So we're going to end up with a graph something like this. Really steep as we get close to 0, and then flattening out as we get further and further out. We get an asymptote. And generally, if you have a graph, a potential energy graph with an asymptote, that asymptote is really the most important single value of the whole graph. And since we're free to choose where we put the R-axis, we're free to choose what energy value we call 0. It generally makes the most sense to call the asymptote 0. So we can basically shift this around to make this asymptote the axis. So we're going to redraw this graph using the R-axis as our asymptote. Still going to keep the same shape. We're going to have a steep decrease, then leveling off, getting completely flat at R naught, and then rising again, slowly, then quickly, but then leveling off to the axis as our asymptote. So there's our Lennard-Jones potential graph. This is the potential energy associated with the forces between these two atoms. And note that this corresponds to the forces we've got. On this side, we've got very steep slopes, a very strong force, pointing in the direction of decreasing potential energy. Closer to equilibrium, we've got a weaker force, still pointing towards equilibrium. At equilibrium, we've got no force at all. Over on this side, we've got a force pointing to the left because we've got a positive slope, so that means a negative force. And then getting weaker and weaker and weaker. So this potential energy graph is really all about the forces between the particles. The slope corresponds to the force value. Any questions on that so far? And some standards we typically use for labeling here. The low point here, the lowest point on the graph, is a certain amount of energy below the asymptote. We call that difference in energy, the difference between the low point and the asymptote, epsilon. Which means that this value, the energy value of that lowest point is going to be negative epsilon. That's the minimum potential energy. And that's going to vary from molecule to molecule. Different types of molecules or different types of atoms are going to have differences in energy between asymptote and low point. So epsilon just means the amount of energy for that particular atom. And in the textbook, the equilibrium separation is R equals 1.12 sigma. Yeah, specifically R naught, the equilibrium distance. Sometimes we label the graph in R naught, so we might just say this is R naught, this is 2 R naught, and 3 R naught, and so on. But it's usually more common to label it in terms of sigma, where sigma is the diameter of one atom. So one atom, if you measure its diameter, we're assuming it's circular here, the diameter is called sigma, Greek letter sigma. So we usually measure R in terms of sigma. Like we might say the distance between atoms is 3 sigma, 3 times the diameter. Or maybe half a sigma or 2.3 sigma or something. And it turns out that the equilibrium distance, this sweet spot where the attractive and repulsive forces balance out, happens to be a little bit more than 1 sigma. Because if let's say the distance was exactly 1 sigma, what would the particles be doing if the distance from center to center was exactly 1 diameter? If you take one atom, start at the center, and go exactly 1 sigma, and then draw another atom centered here, what would you
be touching each other?
Yeah, they'd be exactly touching each other. Because if this is the radius is half a sigma, if you take another half sigma, that's another radius. So if the distance from center to center is exactly 1 sigma, that's 2 times the radius, that means the atoms are just barely touching. If they're just barely touching, would you expect attractive force, repulsive force, or no force? If these electron shells are just barely about to overlap. Yeah, this is going to be repulsive. Just barely touching, 1 sigma apart, is in the too close category. They're starting to repel. So 1 sigma is too close, and they're going to repel. It turns out that the equilibrium distance is a little bit further apart than that. Specifically, 1 sigma plus a little bit extra. And that little bit extra turns out to be about 0.12 sigma. So the equilibrium distance is, we've got half of sigma here, half of sigma here, and then a little bit extra. And that turns out to be half sigma plus half sigma is 1 sigma, plus the little bit extra, which is about 0.12 sigma. So R naught is about 1.12 sigma. That's diameter and a little bit extra. So that's our usual assumption, that R naught is about 1.12 sigma. And of course, sigma also varies from atom to atom. Some atoms have a smaller diameter, some atoms have a larger diameter. But by marking the axis in units of sigma, we can use the same graph for every type of atom. We don't have to draw different graphs if the atoms have different sizes. We can just draw one graph, label in units of sigma and epsilon, and then off to the side we can say this atom has so many times 10 to the negative 10 meters for the diameter, and such times 10 to the negative 20 joules for epsilon. So you can just use one unified graph for any type of atom, and then for specific atoms you just need to know what's the epsilon value and what's the sigma distance. 1 sigma on the graph, by the way, is typically where it crosses the axis. So we've got 1 sigma, 2, and then we could label the graph in units of sigmas. We could have 1 sigma, 2 sigma, 3 sigma, and this should be evenly spaced. And then R naught is a little bit past 1 sigma. Any questions on that so far? And you could generally think of sigma as essentially a unit of distance. Sigma is going to equal typically something like whatever times 10 to the negative 20 meters or something around that size. Epsilon is going to be something times maybe 10 to the negative 22 joules. So you can convert these to meters and joules if you need to. But we usually just list it in terms of sigma and epsilon and then do the conversions later if we need to. When the graph crosses the axis, is that the particle's diameter? Yeah, typically the potential energy graph crosses the axis at 1 sigma. And then it hits equilibrium, the minimum here at 1.12 sigma. Any questions on that so far? All right, so let's see what we can actually do with this graph in terms of filling in the other values of energy. I'm going to tidy this up a little bit just to get rid of all the extra markings. Make this a little more accurate. So let's say we mark off in terms of sigma. 1, 2, 3. And then 1.12 sigma will be the equilibrium value. So we know we hit a minimum at this point. We know it's going to go through the axis here. So something like this, and then up and approaching an asymptote. So we should expect the graph to look something like this. That's our graph of potential energy. Of course, the atoms aren't just staying still and having some potential energy. They're also moving. So what other type of energy would you expect them to have? Yeah, they're going to have kinetic energy. In fact, we should expect the particles to be oscillating. They're coming towards each other until they come to a stop because of the repulsive forces, bounce back out, keep going until they come to a stop because of the attractive forces, and they're just going to keep oscillating, is what we should expect here, as if they were two masses attached by a tiny invisible spring. So let's say we know the total energy. First of all, what's the lowest the energy can possibly be here? Yeah, if we go all the way down to PE min, the negative epsilon is the lowest the total energy could possibly be. E total equals negative epsilon is the minimum possible energy. And this is a pretty boring situation because if we just draw in an E total graph at negative epsilon, and by the way, assuming a closed system, E total should be constant. What would a constant look like on this graph? If you're just graphing E total equals a constant, what does a constant function look like on a graph?
It'd be a horizontal line.
Yeah, it's just going to be a horizontal line because it's the same value, same energy everywhere. So one possibility for E total is just a flat line at negative epsilon. But as I said, this is going to be a pretty boring situation because the particles aren't really doing much. If we wanted to graph kinetic energy, we can always go back to conservation of energy, that E total equals kinetic energy plus potential energy, and E total we're assuming is a constant. If E total is negative epsilon and potential energy is also negative epsilon, what would kinetic energy have to be? If E total and potential energy are the same value, yeah, kinetic energy has to be 0. So at that location where they intersect, where E total and potential energy intersect, at that R value, kinetic energy would have to be 0. If you go to the left, potential energy increases, so kinetic energy would have to decrease, but kinetic energy can't be negative. If you go to the right, potential energy would increase, so kinetic energy would decrease, but again, kinetic energy can't be negative. So the entire kinetic energy graph is just this one single point at R0, 0. Which means what are the particles doing? If the kinetic energy is 0 and that's the only point on the whole graph, how would you describe the particle's behavior? Yeah, it's motionless. All we've got here, this situation is describing two particles exactly equilibrium distance from each other and at rest, just staying still forever. Which really means it's describing a system at what temperature? Yeah, this is 0 Kelvin. No motion, particles at rest at equilibrium distance. This represents a system where the temperature is 0 Kelvin. Absolute 0, the coldest it can get. There is no motion at the microscopic scale. Physically, I don't think this is even possible. There's always going to be some motion, But talking about the idea of absolute zero temperature, this is in theory what that means. No motion of the particles at all. It's so cold the molecules are not even wiggling. In that case then, what would we say about the thermal energy? Yeah, thermal energy would be zero. There's no thermal energy at all. So at this lowest possible case, extreme low energy, we've got temperature equals zero, so thermal energy is zero. But we don't want to say there's no energy at all, because what other type of energy do we have? Yeah, we've got bond energy. So we've got no thermal energy, but we do have bond energy. And since we assumed the total energy was negative epsilon, all that energy is bond energy. So E bond would be negative epsilon, at least negative epsilon per pair. If you just got one pair of atoms at rest at equilibrium, their bond energy is negative epsilon. If you've got lots of atoms, you'd have to take negative epsilon multiplied by the number of pairs. Not the number of atoms, but the number of pairs. And that would tell you the bond energy. But then let's say you add some energy. Let's say you raise E total up to some intermediate value. Let's say negative 1/2 epsilon. So we're going to increase E total to, let's say, negative 1/2 epsilon. So new E total value, which means we're going to have to redraw the kinetic energy graph. And in this case, going back to the idea that E total is kinetic energy plus potential energy, what's probably the easiest kinetic energy to investigate, the easiest value of kinetic energy to look at? What would be the easiest number to plug in for KE? Or to put it another way, are there any extremes? Are there any values that kinetic energy can't be more than or can't be less than?
Well, it can't be less than zero, right?
Kinetic energy cannot be negative, cannot be less than zero. So it's very useful to look for locations where the kinetic energy is zero, because that puts limits on where the particle can be. So if we want to know where the kinetic energy is zero, let's see what happens. You plug in zero for kinetic energy, you would get E total equals zero plus potential energy. So if you want to know where does the kinetic energy equal zero, you should be looking for locations, that is R values, where E total equals potential energy. And how many such locations do we have on this graph? Yeah, we've got two. Any location where E total equals potential energy, that just means a location where the potential energy graph and the E total graph meet. So comparing those graphs, we've got potential energy and E total meet here. That is at this in between R value. And also they meet again here at this R value. So those two R values would be R values where the kinetic energy is exactly zero. At this location and at this location, the kinetic energy is going to hit zero. And where would you expect kinetic energy to be at its highest? Yeah, when the potential energy is lowest, kinetic energy is highest, because we've got a closed system and these are the only types of energy involved. When potential energy goes really far down, kinetic energy has to go really far up, so they balance out to the same total. And that looks like it occurs at equilibrium. So we get the highest kinetic energy at equilibrium. That is, the molecules are going fastest as they pass through the equilibrium location. And that's true whether it's passing through equilibrium on the way in or passing through equilibrium on the way back out. Either way, they have the fastest speed as they pass through equilibrium. And we can even calculate how high. the potential energy would be. Solving this for kinetic energy, we get kinetic energy equals E total minus potential energy. In other words, the difference. Because if you're subtracting E total minus potential energy, you're really just looking for what's the difference between the total energy and the potential energy at that location. So this difference is the value of kinetic energy at that location. So we can just take this difference and transfer it as a kinetic energy value. So that, we have that a little off there. Something like that. And we could even calculate the value. Negative 1/2 epsilon minus epsilon would be positive 1/2 epsilon. So that's the value of our maximum kinetic energy. And if we look at what's going on in between those, let's say we start at this leftmost point. If you go a little bit to the right, what happens to potential energy? Yeah, from here, we go to the right, potential energy decreases, so kinetic energy has to increase at the same rate, so they still add up to the same constant. We keep going to the right, potential energy levels off to a minimum, so kinetic energy has to level off to a maximum. After that, potential energy increases, so kinetic energy has to decrease. In fact, it's just going to look like an exact mirror image of this portion of the potential energy graph. Hypothetically, we could keep going. Potential energy increases further, so kinetic energy should decrease further. But why can't we fill that in?
You can't have a negative kinetic energy.
Exactly. Kinetic energy cannot be negative. So if kinetic energy would dip below the axis, we just stop there. Sometimes we would draw that in as a dotted line, showing the fact that the complete kinetic energy graph mathematically should just mirror the potential energy graph completely. But you would then cut off anything below the axis because that's not actually going to happen. So the complete kinetic energy graph would actually be just this portion. Any questions on drawing that graph so far? And compare this to other types of energy. Are there any other potential energy graphs we've looked at where the kinetic energy looks like this?
That'd be the spring mass. Right?
Yeah, if we go back to the spring potential energy, and that X versus energy, for the spring, the potential energy was a parabola. If we try the same approach, we draw in an E total at some value. We look for locations where potential energy matches E total. At those locations, kinetic energy's got to be 0. We look for the minimum potential energy. That corresponds to maximum kinetic energy. And in between, we fill in the mirror image of that portion of the potential energy graph. So that would be the corresponding graph for object on a spring. Compare these potential energy graphs. Does the spring potential energy graph look like the Lennard-Jones potential energy graph? Are these the same graph, the blue potential energy curves? Not really the same graph, right? I mean, this looks kind of like a parabola in the lower zones, but a parabola doesn't get steeper and steeper without limit like this, and a parabola doesn't level off to an asymptote like this. So the potential energy graphs do not really look the same. They're not the same function at all. In fact, the kinetic energy graphs aren't exactly the same. This kinetic energy graph is exactly an upside down parabola. This one is not quite a parabola, but it looks close enough. The fact that these kinetic energy graphs are very similar to each other means that the particles' motions will exhibit almost the same behavior as if they were connected by a tiny invisible spring. So even though the potential energy graphs are radically different, the fact that the kinetic energy graphs resemble each other means that the particle's behavior will resemble the behavior of a mass on a spring. So even though the particles aren't really connected by a tiny invisible spring, it's just a combination of the electric forces and van der Waals forces and some other stuff, they behave as if they were connected by a tiny invisible spring. So we can use what we already know about spring behavior to make some educated guesses about molecule behavior. If you do just take a spring, stretch it out, and let go, what would you expect to happen?
We'll start oscillating.
Yeah, it's going to oscillate, represented by the fact that it's at a stop, then it gets faster and faster and faster, then slower and slower and slower, comes to a stop, bounces back out, faster and faster and faster, slower and slower and slower, comes to a stop, and just keeps oscillating back and forth. Because the graph of the kinetic energy looks the same here, we can expect this, or almost the same, we can expect matching behavior from the particles. Maybe they start off really far apart, they start attracting each other, getting faster and faster and faster, fastest at equilibrium, and then slower and slower. So we're going to go faster and faster, then slower and slower, come to a stop at this lowest possible R value, then bounce back out faster and faster, then slower and slower, come to a stop, and just keep oscillating back and forth. In fact, we usually call these locations R max and R min in terms of the R values there, because R max represents the furthest the particles can get before they fall back towards each other, and R min is the closest the particles can get before they bounce back out from each other as they oscillate. Any questions on that so far? Now, if we take a look at what's happened here, we've added from, compared to the original situation, the really boring case where we were down at the lowest possible energy, we've added some energy here. We've gone from the original E total up to a new E total. We've added a delta energy. And we might call that heat, we might call that work. If you imagine you grab these particles with teeny tiny tweezers and pull them apart and let go, we could consider that work because you're applying a force as you move them a distance. More realistically, you're just adding heat to the substance and causing the individual molecules to gain energy. But either way you look at it, you're adding energy to make this happen. On the microscopic scale, in terms of the molecules themselves, have you added kinetic energy or potential energy? Would you say the molecules have higher kinetic energy than they used to, or higher potential energy than they used to, or both? Yeah, it really is both. Because if you look at the behavior, originally at the lowest possible energy, they had no kinetic energy. Now they have some kinetic energy. Well, sometimes none, sometimes lots, sometimes in between, because they're moving around. They're changing how much kinetic energy they have as time passes. But on average, they have some kinetic energy. Average is probably somewhere between these. We've got as low as 0, as high as 1/2 epsilon. Average is going to be, let's say, halfway between, 1/4 epsilon. As for potential energy, in the original low energy situation, the potential energy was just negative epsilon forever. But by adding this delta energy, we've increased the potential energy as well. As the particles oscillate around, sometimes they have really low potential energy, sometimes higher. It's going to be oscillating. So on average, we've increased the kinetic energy, and on average, we've increased the potential energy. So we really need to say that the energy we've added increases both the average KE and the average PE of the system. Any questions on that so far? And we could really say that's half and half. The energy we've added, so we could say the delta E total the delta kinetic energy on average is half the energy we've added. The delta potential energy on average is the other half of the energy we've added. If we look at this microscopically, what happened to the bond energy? That's another good question we should look at, because we can really look at this in two ways. The energy we've added, you can consider it in terms of the kinetic and potential energy of the individual molecules as they oscillate. So that would be a microscopic viewpoint, the behavior of the individual molecules. Or you could look at this macroscopically, ignoring the molecules themselves. If you just look at the whole substance, what has changed about the substance? If you just take this substance and make the molecules start vibrating, what have you changed about the substance as a whole? Yeah, you've changed the thermal energy. Making the molecules vibrate faster, or start vibrating when they weren't vibrating at all, means you've raised the temperature. The temperature is really about how much the molecules are vibrating. So making the molecules vibrate faster means you've raised the temperature, increased the thermal energy, and have we changed the bond energy here? No, we haven't changed the phase. You only change the phase if you break some bonds, if you change some particles from oscillating near each other to moving far apart. We haven't caused that transition yet. We haven't broken any bonds. So there's no change in bond energy associated with this delta E. It's only a change in thermal energy. So we can think of this as a delta E total, which is a combination of both kinetic energy and potential energy. But it also could be thought of as just changing the thermal energy. So we can really say the change in kinetic energy is half of the change in thermal energy. The change in potential energy is half the change in thermal energy. The thermal energy we've added splits into both a change in average kinetic energy and a change in average potential energy. And it's an even split, half and half, with no change in bond energy at all. And bond energy only changes, let's see what happens when we raise E total even more. So at this E total level, we've got this kinetic energy graph. But let's see what happens if we raise E total even more. I'm going to leave what we have so far as a dotted line so we can make comparisons. But let's say we raise E total to, let's say, maybe -1/4 epsilon, or -1/10 epsilon. Let's go to an extreme. -1/10 epsilon. Which means we might need some more axis up here as well. In fact, let me mark off a few more markers here. If we raise E total up to -1/10 epsilon, then we want to start by looking for where kinetic energy is 0. So we look for any locations where E total crosses potential energy. We've got one here. So that's a location where kinetic energy reaches 0. That would be R min. Will we have another location where potential energy reaches E total? What's happening to the potential energy graph as we go further and further to the right? Potential energy is going to be approaching what asymptote? Yeah, potential energy is approaching 0. And we may have to draw the graph further out. But potential energy is getting closer and closer to 0. So as long as E total is less than 0, E total will eventually hit potential energy. There will be some R max, even if it's really far out, where the kinetic energy hits 0. And then we could even draw out the values in between. Once again, the maximum kinetic energy is going to appear where potential energy is minimum. Note though that the difference here, what's that difference going to be? The difference between E total and the minimum potential energy. That should be the value of kinetic energy. And that difference, if we subtract -1/10 epsilon minus epsilon, becomes +9/10 epsilon. So that's going to be almost at positive epsilon. So that's our max kinetic energy. And again, if we draw out the graph, from here, from R min going to the right, potential energy is decreasing steeply, then levels off to a minimum. So kinetic energy increases steeply, levels off to a maximum. And thereafter, potential energy increases slowly, then kind of quickly, then levels off towards an asymptote. So kinetic energy also has to decrease slowly, then kind of quickly, then level off towards an asymptote. Mathematically, the asymptote would be approaching -1/10, approaching E total. but it never gets there because as soon as kinetic energy hits 0, we have to stop. So there's our new kinetic energy graph at a E total level almost up to 0. Does this graph still look like a parabola? No. Near the middle, it kind of resembles a parabola, but on the left side, it gets way too steep, way too fast. And on the right side, it approaches an asymptote, it levels off. A parabola does neither of those things. That tells us that at higher energy levels, these particles no longer act very much like they're connected by a spring, or at least not by a normal spring. You could treat this as this weird magic invisible spring that gets really strong when they're close and gets really weak when they're further apart. So these particles, they still count as bonded. They're still a closest they can get to each other and a furthest they can get from each other. There's still an Rmax and an Rmin. They can only exist between those values. But they snap in really close, really fast, and then spend a lot of time drifting at low speed out in the outskirts, and then gradually come back together, snap in really close, and then drift out again. So they're spending most of their time lazily drifting slowly out in the outer reaches. So it doesn't really behave all that much like they're connected by a spring anymore, but they still count as bonded. And note that by increasing this, we've still increased the average kinetic energy, and we've increased the average potential energy because the potential energy can go higher now. So the energy we've added still counts as, it still all counts as delta E thermal because we've just raised the temperature. We haven't broken any bonds yet. Of that delta E thermal, we still have half of it goes into raising the average kinetic energy and half of it goes into raising the average potential energy. If we raise it a little bit higher though, and note by the way that we've made Rmin a little bit closer. We're allowing the particles to get a little tiny bit closer together, but Rmax has changed by a huge amount. They're able to get much further apart. And this corresponds to the idea, if you've got lots of particles and they're all able to get further apart, what would you expect to observe about the substance as a whole? If you've got this cluster of molecules and it's now hotter and all the particles are able to get further apart, what would you observe? Is it a gas yet? Have we broken the bonds here? We haven't broken the bonds, so it doesn't count as a gas. This is still a solid. But what happens if it's still a solid, but the molecules are all a little bit further apart? What would that do to the whole object? If you take an object and make all of its molecules further apart, what would you observe? Still not melting though, because that's a phase change. That still involves particles breaking bonds. So it's still a solid. But, you know, a solid's mostly empty space anyway, right? It is definitely changing temperature. We're raising the temperature, allowing the molecules to vibrate faster. But if this solid is mostly empty space, it's just atoms and empty space in between. If you expand the empty space, the whole object is going to get a little bit bigger. And this is what physically happens. If you take a solid object and heat it up, you're raising the temperature and you're also going to expand it slightly. The object is going to get a little bit bigger as it gets hotter. And for most objects, this is such a small change in size that it's not really all that noticeable. But it can make the difference between, for instance, let's say you've got a jar lid that is stuck on the jar and you can't unscrew it. If you heat up the lid, the metal of that lid is going to expand slightly, and that might make it easier to unscrew the lid. So running a stuck jar lid under hot water can often make it easier to unscrew because the heat is making the molecules get a little bit further apart as you expand Rmax. On the other hand, if we raise the E bond even further, let's say we add just enough energy to raise E total all the way up to 0. Raise E total all the way up to 0 or higher. We now have a location where E total hits potential energy, so that's our new Rmin. Where does E total hit potential energy again over here? If we keep going further and further out, how far do we have to go before potential energy hits our new E total of 0?
It's never going to hit the E total of 0.
It doesn't. So we still have an Rmin. The Rmin is a little bit closer in, So we now have no Rmax at all. And that's why we would call this unbonded. If we raise E total all the way up to the asymptote, in this case 0, the particles do have an Rmin. There's a closest they can get at that energy level. But when they bounce back out, there's no Rmax. They don't fall back towards each other. They just keep going forever and ever. They do get slower and slower. Kinetic energy is going to get closer and closer to 0, but they never come to a complete stop. And that's what we would call an unbonded pair of particles. Raising total energy high enough that there is no longer an Rmax, in this case, just raising E total up to 0, means you have broken the bond. And that's where the phase change comes in. If you raise an energy high enough that all the particles break their bonds, you've converted it to a gas. Liquid is this weird in-between state where you've added enough energy to break some of the bonds, but not all of them. Where some of the particles are now unbonded, but some of them are still bonded. So they're more free to move, but they can't really leave. And if you're dealing with just two particles, you don't really have a solid liquid gas distinction. With two particles, either they're bonded or they're unbonded. If you got lots of particles, they could have very closely bonded, they could be partially bonded, or they could be unbonded. So that would be solid, liquid, and gas. Lots of bonds, only some bonds, and no bonds at all. But for just a single pair of particles, it's either bonded or unbonded. And what happens when you keep adding energy? Once you've unbonded it, if you add more energy, let's say you raise E total up to like 1/4 epsilon. In that case, Rmin would be a little bit closer in, but not all that much closer in. PE, or kinetic energy max, would be even higher. And then it would drop. But instead of dropping to 0, what would the kinetic energy approach? Yeah, kinetic energy is going to approach E total. Again, if we go back to conservation of energy, kinetic energy is E total minus potential energy. As potential energy approaches 0, kinetic energy approaches E total. So kinetic energy is going to approach E total as an asymptote, which means if you raise E total even higher, the kinetic energy, the particles are not only able to keep drifting apart, they keep going at a fairly decent speed. If E total is exactly 0, the particles can keep going further apart, but they get very, 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 very slow. Higher E total means they're able to still keep going fast. So when you get E total up to 0, you've broken the bond. You've turned it into a gas. Raise E total even higher, and you've just made the gas hotter. Higher temperature in the sense that the particles are able to move faster. And would the amount of PE left be negligible? Yeah, once you've broken the bonds, you can assume the particles are now going to be very far apart from each other. The further apart they are, the closer potential energy is to 0. So for a gas, we assume potential energy is 0. But note that that's not a loss in potential energy. We're not starting with some positive potential energy and losing it. We're starting with a negative amount of potential energy and bringing it up to 0. So a solid or liquid, a bonded state, would have a negative quantity of potential energy. To break the bond, you raise the energy, bringing the potential energy up to 0. So a gas would have 0 potential energy. When E total equals 0, it can have kinetic energy, but typically once we break the bond, we would assume the particles are very, very far apart. So E total being 0, we would expect the particles to probably be far apart and moving very, very slowly. So they would have some kinetic energy, but on average, they'd be very far apart with very, very little kinetic energy. So that would be essentially a gas that's just barely at the phase change temperature. You've raised it up to the phase change temperature, added enough energy to break all the bonds, but you haven't heated it up beyond that. Any other questions on that? All right, sounds good. If you want to get some more practice on this, try drawing out some Leonard-Jones potential graphs of your own, choose an E total value, and try drawing the kinetic energy that results from that E total. Try various values below 0, various values above 0, and watch for what the difference between those is. Look for what's changing. If you add a little bit of total energy, what happens to everything else? And also try this with some other graphs. Maybe just make some squiggle function to call potential energy, draw in an E total value, and see if you can draw the kinetic energy for that E total. Good way to get some practice with how these graphs work. So give that a try, and we will look at some more examples next time. You're welcome.